in continuation with the significance of the numbers in your conduction due to the heat transfer. The Reynolds number, that is nothing but your d into velocity u into the rho upon the mu. So this is representing the inertial force upon the viscous forces. Now how this Reynolds number is representing the inertial force upon the viscous forces. Now when you talk this viscosity mu divided by the rho, that becomes your kinematic viscosity. That is mu upon rho is your kinematic viscosity. Mu upon rho, this is equals to your kinematic viscosity. Kinematic viscosity, which is equal to the mu upon rho. These are having the units of meter square per second. Newton second, kinematic viscosity meter square per second. So this is the viscous forces, kinematic viscosity in terms of the viscous forces. And these are your inertial force, that is represented as rho v square average upon L square. So at larger Reynolds number values, this inertial forces, they are having the higher values. Inertial forces, they are having the higher values. That means these inertial forces represent to the density, velocity and length. So these inertial forces, which are proportional to the fluid density and the square of the fluid velocity, are large relative to your viscous forces. And thus the viscous forces cannot prevent the random and rapid fluctuations of the fluid. That means the viscous forces cannot prevent this rapid fluctuations. Rapid fluctuations, that means the turbulence. Turbulence that cannot be prevented. So we call this as the turbulent flow condition. So viscous forces, when they are not able to prevent or they are not able to reduce this value of the Reynolds number, then we are saying that there are fluctuations, that is in the turbulent region. So viscous forces, they are not predominant. That means they are not having the higher values. That is why you get the higher Reynolds number values. And so we are taking into account the Reynolds number values more than 10,000, that is considered to be the turbulent region. So at smaller or moderate Reynolds number values, that is below 10,000, the viscous forces are large enough to suppress these turbulent fluctuations. That is nothing but your laminar region. So the Reynolds number at which the flow becomes turbulent and the flow is laminar. That is what is represented by the inertial force upon viscous forces. Prominently, these viscous forces, they decide the value of the Reynolds number. So this is all related to the Reynolds number. Then then there is a Piglet number. So this Piglet number, that is nothing but the Reynolds number into the Prandtl number. So what this represent Piglet number is Reynolds number into the Prandtl number. That is du rho upon mu is your Reynolds number and Prandtl number is Cp mu upon K. So this is the Piglet number, that is nothing but your Reynolds number into the Prandtl number. So that is the ratio of mass heat flow rate by convection upon the heat flow rate by conduction under unit temperature gradient through the thickness L. That is the Q convection So this Grashof number that represents the natural convection effects in momentum equation, that is incorporating G beta delta T L cube into kinematic viscosity square. This is kinematic viscosity is having the units of meter square per second. L is your characteristic length and beta is the coefficient of thermal expansion. So this Grashof number provides the main criteria in determining whether the fluid flow is laminar or turbulent in natural convection. So Reynolds number, that is going to give you the turbulence criteria also. And this Grashof number, that is also providing the main criteria in determination whether the fluid flow is laminar or turbulent in natural convection. That is what we have differentiated the Nusselt's number, which is a function of Reynolds number, into Prandtl number, that is corresponding to the forced convection, and in case of free convection, Nusselt's number, that is equal to the function of Grashof number and Prandtl number. That is what it represents the turbulence and the laminar conditions in case of a natural convection. So when the surface is subjected to the external flow, the problem involves both the natural and forced convection. The natural convection effects are negligible if Grashof number upon Reynolds number square is very less than 1. Then the free convection dominates and the forced convection effects are negligible if Grashof number is less than Reynolds number square. So the Grashof number is a measure of the relative magnitude of the buoyancy force and the opposing viscous forces acting on the fluid. Then the Raleigh's number. Raleigh's number, that is incorporating the Grashof number into Prandtl number, which is equal to the Nusselt's number, but the natural convection heat transfer on the surface depends on the geometry of the surface as well as its orientation. Natural convection, geometry of the surface as well as orientation, the variation of temperature on the surface and the thermophysical properties of the fluid, they are involved. So, with the exception of some simple cases, the heat transfer relation in natural convection are based on experimental studies and they are incorporating this Raleigh's number, that is the constant C and N depends on the geometry, the constant C and the N, that is depend on the geometry and the flow regime, whether it's a laminar or turbulent flow conditions, depending on that is going to vary, which is characteristics characterized by the Raleigh's number. If the value of N is usually 1/4 for laminar flow condition and 1/3 for turbulent flow conditions. So natural convection heat transfer correlations are usually expressed in terms of Raleigh's number raised to a constant N multiplied by the another constant C, both of which are determined experimentally. So you have to remember this constant of coefficient, constant of exponent, Raleigh's number and Nusselt's number. So that is related to the different numbers and this importance of this